Hey y'all, welcome back to another round of engineering. And yeah, let's go ahead and do some more example problems using the node voltage method. So I've taken a screenshot from textbook or something, just another circuit. And go ahead, take a couple minutes, hack through the problem, see if you can apply the node voltage method in order to solve this circuit for all the currents. All right, there we go. And you notice already that I've made it slightly more tricky. I chose a circuit that has a current controlled voltage source. Okay, so that's a little bit more of a trick here. So, okay, well, let's go at it. So the first thing that we need to identify is we need to find our essential nodes. Okay, places where more than two wires connect. And looking at this circuit, it seems that we have three. I'll label this one A, essential node A. I've got one B as in boy here, and we'll call this one down here, again, highlighting this whole branch, we'll call this C. Okay, so we have three essential nodes. Okay. I am going to go ahead. Well, we found our essential nodes, number one. Number two, we need to ground one of them. We need to choose which one we want to call a reference node. I'm going to use node C, and solely for the fact that it has 1, 2, 3, 4 wires on it. I guess you could count this as 5, but I mean, okay, 1, 2, 3, and 4 wires. So I think that node C will be the most convenient to actually ground. So let's go ahead and ground that. Now, that being the case, now we need to find the voltages for both node A and B as in boy. So let's go ahead. I am going to first of all consider node A. Okay. And now I'm not going to draw my current directions on the figure anymore. Okay, that's one of the other things is that you can start looking at the diagram and writing down the equations directly. So looking at node A, I'm going to start, I will write the potential of node A minus 20. And again, that minus 20 is because I'm looking at this branch over here. And I'm going to divide by 2 ohms. Okay. Now, if I consider this downward branch, actually, let me highlight that. If I consider the downward branch, I have VA. Remember, I've grounded C, so I don't have to subtract anything, over 20. Looking at this right branch, I have VA minus VB, so the difference between the two floors, if you will, divided by 5. And that whole rigmarole, we'll set that equal to 0. All right. So we're done with node A. Node B, as in boy. There we go. Okay. So let's go ahead. Even though we have a dependent supply, let's go ahead and apply node voltage like we would for any other situation. Okay. And then we'll take care of that dependent supply in a moment. So let's go ahead. If I consider this left branch right here, I have something that says VB minus VA over 5, excuse me. 5. There we go. Now, in addition to that, I have this lower branch, and we have VB divided by 10. And lastly, we have this right branch. So I will put VB. Now notice, again, I've mentioned this is a voltage supply, right? So as I cross over, I've got to subtract, and I have this 8 I phi. That's the value of that voltage drop. And I have a resistor in that circuit, that branch, excuse me. And so I will set that all equal to 0. Now you say, well, Greg, what do we do about this? We have this I naught now. We were supposed to get rid of the I's. And I say, yes, that's correct. Notice that this circuit shows us the branch where I naught is, or excuse me, I phi. Okay. So whatever the current is through this 5 ohm resistor, that's the current that I use here in the current controlled voltage supply. Okay. But we have an expression for that I, right? That I phi, in fact, we've used it already right here. Highlight, boom. And we used it here, boom. We have I phi, that is equal to the potential difference between VA and VB divided by 5. Okay. So what I want to say is that when we have a dependent supply, we can go ahead and still write our node voltage equations, just like we normally would. How we take care of the dependent supply is by a third equation, which, if it's a current controlled supply, then we substitute in our Ohm's law for the current. If it's a voltage controlled voltage supply, then we just write in our regular voltage drop. Okay. Now you might ask yourself, how did I know that I should use VA minus VB instead of VB minus VA over 5? And I would say the key comes back into the fact that we are shown the direction that the current is flowing, and it's away from node A. Okay. Remember, node voltage, the first potential is the node that the current is moving away from. Okay. So this top equation is correct, or excuse me, this top equation matches the direction that we're given in the figure. Okay. So we'll get rid of that guy. Okay, so that's the no. So if we substitute this in, we have something like, I'll leave everything else untouched for right now, VB minus VA for 5 plus VB over 10 plus, now we got to be careful here, don't want to make any mistakes, VB over 2 minus, now we have 8 over 2, that's 4. So we have 4 times I phi VA minus VB over 5. And that whole rigmarole equals 0. Okay? So let's go ahead and I'll rewrite this on the next page and we can go ahead and solve. So I've taken the liberty of rewriting this, and now we're in a position where we can go ahead and substitute it into a matrix, or you could probably sub and solve since it's only a 2 by 2. That's fine. I'll go ahead and write it in matrix form, an augmented matrix. Okay, so we're at a point where we can say what the potential of VA and VB are with respect to ground, which is at VC. And what we get here, let me go ahead and check my handy dandy calculator. I get something like 16. Did I get this? I get something like 16 volts and 10. Okay. And so now we can go through and find all of the currents in every branch on the circuit. Right? We have things like, well, let's go back and check. We have now VA is 16. Okay? VB is 10. So let me go ahead. What I will do, keep. Let's just go ahead and take this and copy this to another page. So now that I know that VA is 16 volts right here, and VB is 10 volts, okay, now I can find the current through all the branches. For example, the current through the 2 ohm resistor is 16 minus 20 divided by 2, right? This was VA minus 20 over 2, so this would be negative 2 amps. That should make some sense. We called this bottom branch ground. So we go up 20 volts, and this is only 16. So we should flow from high to low in terms of our current. Well, okay, so we'll go ahead. I-20 should be 16 over 20. Okay. So what do we have? We have 8 tenths, so 0.8 amps. And okay, let's go ahead. We'll just do the whole rigmarole. We have VA minus VB over 5. And so we get something like 1.2 amps. Right, 6/5. Well, let's go ahead. I-10 is the potential of B divided by resistor. Right? And lastly, why don't we go ahead and figure out the current through the 2 ohm. Okay, so we'll call it 2, and I'll call this one B. So maybe I should have called this first one A, just to distinguish the two. So what do we have here? We have VB, which was 10, minus the potential drop across this current, or this voltage supply. So we have 8, and I've problem called that I-phi. So we have 8 times 1.2, all divided by 2. Okay. So let's see, this would be equal to, I got to think about this for a second. This would be equal to 10 minus 9.6 all divided by 2. So at the end of the day, we get something like 0.2 amps. And boom, we're done. And we should probably double check to make sure that everything matches up. So it's always good to sanity check. So these 3 deal with node A. And indeed, we see that 2 go in, 2 amps goes into node A, and 2 amps comes out. Okay, everything works out there. Now these 3 right here deal with node B. And we see that 1.2 amps flows into node B. Okay. And we see that 1 amp flows through the 10 ohm resistor, and 0.2 amps flows out through the 2 ohm resistor. So again, current is conserved. So boom, we've got our answer. Pretty cool, huh? Okay, well, let's go ahead. Let's try another one. Let's apply node voltage to this circuit. Okay. So go ahead, take a minute, hack it out. Got it? Good, 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 good. So let's go ahead and walk through and get the answer. So I am going to label my nodes. Okay. So I'm just A, B, C, D, and I'm going to go ahead and ground D. And if I ground D, I have a question for you. What's the potential at A? And hopefully you see this is 50 volts. 50 volts. Okay. Two reasons, or at least the combination of two reasons. I grounded D, and there's only a potential source between D and A. No resistors, for example. So immediately, if I set D equal to 0, and the existence of this independent potential source means the voltage at A is 50 volts. So boom, I've already solved for one of those. Okay, well, let's continue forward. Let's go ahead and consider node B. And if I take the left branch, I have something like VB minus 50, right? The potential at A divided by 5. And I'll kind of put in parentheses here. This is I phi, right? And then coupled with that, let's take the lower branch. We have the potential at B divided by 50. And then we have another incident or instance that we have to consider. We have this branch between B and C that has a current controlled voltage supply. We're going to have to figure out how to deal with that. For illustrative purposes, I am going to say that the current through this branch, I'm just going to label it as I, and I will have it going from B to C. Okay. So I will just call this I for a moment, equals 0. Let's go ahead and write down an equation for C. And again, the leftmost branch, we have that current I that we put in there, and it's running into node C, so I better put a negative I. The bottom branch, VC over 100. Okay. And then the rightmost branch, we again see we have a current supply pushing current into node C. So we better put a negative sign in there, and we have 4. And that whole rigmarole equals 0. Okay. Now here's the reason why I chose the problem. An interesting idea. If I sub and solve, notice that I have an I here. If I go ahead and substitute in to eliminate the I's, go ahead, write down what the resulting equation is. If I take B and C together to get rid of I, and hopefully you see it, I get VB minus 50 over 5, okay, plus VB over 50. Then, right, I move the I to the other side. I get plus VC over 100 minus 4 equals 0. Now that in itself might not seem too impressive. Here's the piece that I want to emphasize. Okay? If I look at this resulting equation, it is as if I had nodes B and C and combined them together into a single node. You see that? Right, what do we have? We have the potential at B minus 50 over 5. That's this left branch. Then we have VB over 50. That's this bottom branch. We have VC over 100. That's the second bottom branch. And then we have that negative 4 amps going into C. So this resulting equation is as if we took nodes B and C and somehow combined them together. That's a special situation that the book, and pretty much any book, will refer to as a supernode. Supernode. It's a very particular circumstance where you can take two nodes on your figure in your circuit and combine them together. Treat them as a single node. It helps you write down the equations faster. Now here's the case. Okay, I said a particular circumstance. Here's the specific instance when that circumstance arises. Anytime you have two nodes separated by a potential source, and I should say only a potential source. Okay? So you can't have a resistor in that branch. You notice the last example we ran, there was a resistor in the branch with the potential supply. So this supernode idea doesn't help. But here, you're okay. So you can treat B and C as if it were a single node. And the only other thing that you need is the relationship between the potential at B and the potential at C. So let's go ahead and write down that relationship. So for lack of space, I don't want to flip pages yet. I'll go ahead and do it up here in this upper right. Okay. And we see that we have the potential at B plus 10 I phi is equal to the potential at C. And of course, we have an expression for I phi, so let's go ahead and substitute that in. VB is equal to, excuse me, not equal, VB plus 10 times the quantity. We had I phi highlighted here. VB minus 50, the potential at A, divided by 5 equals VC. We could go ahead and simplify this. We have something that tells us 3VB minus, okay, 50, 100. 50 divided by 5 is 10. 10 times 10 is 100. So we get 100 equals VC. There we go. Cool, huh? Okay, so let's go ahead and we have two equations now. We have the relationship between the potential at B and the potential at C. And then we have this equation that came from either, you could say, combining the node voltages at B and C to eliminate I, or alternatively, we could just call it the equation that came from the supernode. So we will go ahead and solve these two equations. Next page. All right. So I've taken the liberty of rewriting the two equations, and now it's just a matter of personal preference. You can sub and solve, you can do the matrix stuff. Right? So we're free to reign. So, yeah, I guess, okay, well, I'll set up the augmented matrix. So you have VB, 1/5 is 0.2, and 1/50th would be 0.02. So we have 0.22. So 1/5 plus 1/50th. That'll give us VB. We have 0.01 for VC. Right, divided by 100, and that whole thing should equal 14. Down here we have 3, -1, and 100. And now we are free to figure out what the values are. And so what I get is something like VB is equal to, well, we have VB and VC. I get VB is equal to 60 volts, and VC is equal to 80. And of course, we have VA. Go ahead and write that in there to remind us. VA is 50 volts. And now, of course, I'll leave it to you, but now that we have the potentials at each of the nodes in the circuit, we can go ahead and find the current flowing through each of the individual branches. Cool, huh? Good, 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 good. Okay. Well, how about another example? Boom. Go ahead. Take a minute. Go at it. You got it? Good, good, good. Okay. Let's go ahead. So we have our node. I'll call that one A, this one B, call that one C, and this one D. And I'll go ahead and ground D again. And yeah, let's go at it. Well, right away, because I grounded D, we can say that VA has to be 10 volts. Okay. Straight away. And we see that we might have a little bit of trouble. Our current controlled voltage supply depends on the current going through A, or going in through the 10 volt source. Okay. So why don't we go ahead? I will, yeah, let's go ahead. Let's consider B as in boy for a moment. And let's get an idea about what the current stuff is for that one. So we have VB minus 10, right? The potential at A over 100. 10, excuse me, not 100. And that comes from the left branch. We have the bottom branch where we have plus VB over 40. And then we have the right branch plus VB minus VC over 20. And that whole rigmarole better be equal to 0. Right? Good. Okay. Well, how about, let's see here. Well, we have some sort of relationship between the potential at C and the potential of D, right? Namely, VC must be equal to minus 20 I delta, right? Based on this, right? Ground is the high side, which means C has to be below the ground, the basement, if you will. Okay. Well, let's go ahead. It looks like let's go ahead and consider node A. And I highlight we might have a little bit of problems here, but let's go ahead. I delta is going into node A, so we'll write that as I delta. And then the current going out, we have the right branch, 10 minus VB over 10. Then we have this top branch, 10 minus VC over 30 equals 0. And now we are golden, right? Let's take a look. We've got 3 unknowns, VB, I delta, and VC. Okay. And 3 equations. So we can go ahead and form our matrix and sub and solve. Of course, I guess you could just take this and plug it in here and get a 2 by 2. We'll go ahead and write down a 3 by 3. So I'll use that in the upper corner here. So I'll move VC equals negative 20 I delta. Put that right there. Okay, so let's go ahead and write down our augmented matrix. And I'll use the first column as VB, the second column as VC, the third column as I delta. And just keep our stuff straight. So VB, we have 1/10 plus 1/40 plus 1/20. Okay. That takes care of that one, that one, that one. For VC, we have minus 1/20th. And no i's, so we have 0. And then we have negative 10 over 10, which we move to the other side. So we get 1. Second equation. Well, okay, we have negative 1/10 for VB right here. We have negative 1/30th for VC. So I put negative 1/30th for VC. That would take care of this one right there. And we have negative 1 for I. And what do we have left over? We have 1 plus 1/3. So that gives us 4/3. And again, standard form, we'd have to move that to the other side. So we have negative 4/3. Lastly, okay, we have no VBs. We have 1 VC, and this would be 20I, and that would be 0. And there is our augmented matrix. So let's get an answer for VB, VC, and I delta. And so what I have at the end of the day is something that says VB is 24 volts. I have VC is 64, and I delta is negative 3.2. So this negative I delta gave me pause for a few minutes, and then I realized, yeah, what's going on here is that even though we took I delta to originally be running into node A, as indicated by the problem, in reality, it's actually running away from node A. So that's hence the negative sign. And if we go through and we kind of hack through the rest of it, that would mean that instead of node C being below ground, it's actually the highest potential. It's 64. So I'll put 64 volts here. And what does that mean? It means that current runs from high to low. And so if we go through and hack out the currents, we'll find something like this. Current is 2 amps running to the 24 volt potential. In fact, I'll get rid of the nodes here for a minute. Okay. And this current running through this branch, went through and hacked it out. What did I get? I got 1.8 amps. 0.8 amps. Okay. Okay. And then, yeah, we keep going. And, well, yeah, I'll just go ahead and throw in the rest of these. The current running through here I got as 1.4 amps. And so you see that you have 1.8 amps and 1.4 running into node A, which means that this current should be running not into A, but out of. This should also make some sense since node B was at a higher potential, node C was at a higher potential. That means that current should be forced onto node A from those other two nodes. So yeah, it gave me pause for a moment. I was like, what's going on here? But yeah, everything works out. Everything works out. So, okay, convince yourself this is the case. In any case, I think that's all. I'll leave that for you for right now. Of course, if you want, just let me know. I can always run more examples. But I think that that's sufficient for us to get a feel for what's going on. So now what's left to you is to practice, practice, practice. I'll leave it there for right now. Hey, thanks for your attention. I'll see you next time.